This work proposes a novel approach to implement recurrent neural networks, RNNs, in hardware using spintronic oscillators as dynamical neurons. The authors simulate a multi-layer network of spintronic oscillators and demonstrate its ability to perform time series classification using standard machine learning tools. The network architecture consists of successive layers of dynamical neurons, connected by interlayer and intralayer connections. The neurons are represented by the autooscillator model, which describes the dynamics of the dimensionless normalized amplitude x. The model is simplified to dx, dt equals gamma x plus I, t, x, 1x, where gamma is the damping term, and I, t, is the time-dependent drive. The network is trained using backpropagation through time, BPTT, and PyTorch, achieving 89.83 plus or minus 2.91% accuracy on the sequential digits dataset, comparable to the equivalent software network. The authors also demonstrate that the spintronic network can be trained on input timescales over a 5-fold range, centered around a value depending on device parameters. Guidelines are derived to find these device parameters, including the neuron relaxation time, which must be larger than the input timescale, and the cumulative drive, which must be around 1. The network's adaptation to different timescales is studied by training it on series with varying input timescales. The accuracy depends on the time interval between input points, with a maximum accuracy maintained over a wide window of timescales. The network's performance degrades significantly when the timescale is well below or above the optimized point. The dynamics of the spintronic neuron rely on a competition between the current drive and the damping. The relaxation time of the neurons must be larger than the time between two input points, and the cumulative drive divided by the relaxation time must be roughly equal to the damping. The learning rate must also match the input timescale, with faster inputs requiring higher learning rates. Here is a combined summary of the 4 pages. A multi-layer neural network leveraging spintronic oscillators as neurons is presented, utilizing transient dynamics for memory and nonlinearity. The network is trained with backpropagation through time and achieves 89.83% accuracy on a time series classification task, comparable to a standard recurrent neural network. The impact of timescale adaptation on performance is explored, with results indicating optimal accuracy when the cumulative drive is around 1 and the input timescale is larger than the relaxation time. The effect of connection density on performance is also investigated, demonstrating that intralayer connectivity can be reduced to 10% and interlayer connectivity to 20% without losing accuracy. The authors propose using spintronic resonators as physical implementations of the synaptic layer, estimating a network energy consumption of approximately 40 pJ per image. This approach shows promise for time series processing at low energy cost. The paper concludes by highlighting the potential of spintronic oscillators for time series processing and providing guidelines for designing and training such networks. Recent advancements in neuromorphic computing have led to the development of novel architectures and algorithms inspired by the human brain. Researchers have explored various platforms, including photonic recurrent neural networks, mechanical oscillators, and spintronic devices, to implement analog recurrent neural networks. Studies have focused on the use of spintorque nanooscillators for reservoir computing and the application of spintronic devices for neuromorphic computing. Theoretical frameworks and machine learning algorithms have been applied to understand and optimize the performance of neuromorphic computing systems. Limitations and assumptions, such as the need for further optimization and reliance on specific materials and devices, are acknowledged, and future work is proposed to address these challenges.